Okay, great. Welcome, everyone. This is the community meeting where we show off all the features for Gazebo Ionic. Before we get to that, I wanted to share just a few things of news. So we had the tutorial party, and this is the results from the tutorial party. Thank you for everyone that participated. This was a great turnout, definitely much better than last year. We have all the stats here, and even Mac OS and Windows got some coverage. That was great. Appreciate it. Here are the top 10 contributors. As of the cutoff date, there were more contributions after the cutoff date. Those were not included, but yeah, some of you did a lot of issues, so I really appreciate that. You will be getting t-shirts soon. And this is the announcement of today, but here's the graphic for Gazebo Ionic. So feel free to download that and also go to the store to buy any swag. We have various things, t-shirts for adults, kids, yeah, just lots of different things you can buy. So feel free to do that. And then we also have a 3D model that was created by our own Cole Wiesmeyer, who's on this call. Thanks, Cole, as always. We really appreciate you making these. So if you're into 3D printing, you can take this and print it yourself. And that's all I wanted to say there. And then this. The next thing I wanted to share was the Gazebo J naming results. Everybody ready? So we had to vote, and the outcome. Here we go. Gazebo J is Jetty. There was 4 rounds. I think Jam and Juncture were out in the first round. Joyce was on the second round. Sally was on the third. Getty. All right. I think that's all I have to share. Hand it off to hand it off to Ian.
All right. Okay, cool. Hey, everyone. So welcome. This is the time of the year where we present all our features that we worked on in the past 12 months. So as you heard, Ionic release is just around the corner. We're preparing for releases. And one thing that we usually do is we put together a lot of features and demo them. So for the past 12 months, we have been busy. So I'm just gonna, so we have quite a few demos that we're gonna run through today. Each of them are around gonna be up to 3 minutes, some of them being longer, etc. And then we group them by presenters. So I'll just quickly share what we're gonna be going through today. Here we go. So we have 15 presentations, and then we have the presenters all in the meeting right now. So we're going to present all Gazebo features. There are various of them: physics, rendering, GUI, transport, logging, and ROS integration, and also OpenRMF integration work. We have a nice demo with all the 3 OSRA projects combined together, Gazebo, ROS2, and OpenRMF working. And then SDF, and then we also have some help on getting installation working set up with ROS and Gazebo. So it's a lot to get through. All these features should be in Ionic. As usual, we backport features wherever possible to earlier versions if they're API compatible. So some of the features that you see today will also be available in Harmonic as well, but everything we worked on in the past year. So as usual, we get started with Cole to introduce the Ionic demo world that he created. Go ahead, please take over.
Thanks, Ian. Let me present my screen here. There we go. Okay. So this is the demo world for the Gazebo Ionic release. We based on a restaurant called Gazebo in Valencia, Spain. We chose it for the Greek columns, which of course match the theme of the Ionic release. And also because indoor spaces tend to show off global illumination, which Gazebo now supports real-time global illumination. So you can see that although we have mostly downward facing lights, we still get illumination on the ceiling from the light bounces. That light also carries color information, so the blue from the columns and table supports are bouncing their color information onto the surrounding objects. We can also visualize this here with the debug tools, and you can see that we have the bounce light is filling the room. We also get light from global illumination light from the emissive materials as well, which is nice. We also baked an ambient occlusion map for this environment, which is just stored in the GLB mesh file for this world. So GLB is nice. It contains all of our, it's just one file. This has the mesh, the textures, everything we need for this. So you can see in the corners here, for instance, we have nice dark soft shadowing. That's from the ambient occlusion map. If we go to the back of the restaurant here, where it's a little darker, you can see it even more clearly here. And yeah, our lighting setup is fairly simple. It's just 3 downward-facing wide-angle spotlights and a couple of point lights for these column LEDs. And this was all authored in standard mesh editing tools, in this case, 3ds Max and Blender. For collisions, we also, it's a little hard to see with all the polygon fighting there, but we used all simple collisions for this environment to maximize performance as well. All right, so yeah, that's the environment, and yeah, I'll go ahead and hand it back over to Ian.
All right, thank you. So everywhere we create a different type of environment. Last year we had a lake house, we have an outdoor, indoor, and then before that we have warehouse as well. And this year we went with kind of like a cafe, restaurant feel to test different types of robots with different applications. All right, so back to me. I will take over control and I'll present my demo. Share now. All right. Okay, this is coming through. Okay, so the first feature I'm going to be demoing is recently we added support for mesh optimization. So what mesh optimization is that in SDF, where you have a collision and then you have a URI pointing to the mesh, we have now added new tags. An attribute called optimization, where you can actually specify how to optimize the mesh. And there are 2 methods that we support right now. One is convex hull, and then one is convex decomposition. So if you look at this breakfast model here, you look at its collision. This mesh has a exact mesh collision, so no changes done to it. So this is it fits exactly as the visual mesh. And here I'm just going to show you what it looks like with convex decomposition. So let's go view, collisions. So for this particular example, I broke this down into 32 convex hulls. And there's also a resolution parameter that you can set. So I haven't gone to the highest, but this it's a concave mesh that's been broken up into convex meshes. So you can see if I bump up the number of collisions and resolution, I could actually get a nice hull here. Sometimes it's useful for example, in the bullet-featherstone physics engine, we actually use convex hull shapes to represent them for more efficient collision checking. And the other method is just a convex hull. So rather than just have one concave mesh, and then you can just say, hey, I want Gazebo to automatically change this to a convex hull, a nice, simple, optimized collision that will make things faster for you. So these are the features that are available in Harmonic as well, so not just in Ionic. All right, so this is the first feature I'm demoing. The second feature I'm demoing is bullet-featherstone implementation that I just talked about. So we did quite a bit of work over the past few months improving our bullet-featherstone support. When you launch Gazebo, by default, it uses the engine called Dart. So in order to use bullet-featherstone, you have to pass in a command line like --physics engine, and then you specify the bullet-featherstone plugin. So this plugin was already implemented and introduced in Garden, so a few versions earlier, but it was actually just recent month we have made a lot more improvements to it. That includes support for nested models, for better support for meshes I just talked about using convex hull shapes. But one thing that I like to demo that is different from Dart is that it comes with a nice feature called auto deactivation. So if you're familiar with Gazebo Classic, there's an auto disable tag that you can specify. It's on by default, which means when objects are not moving, they're disabled by default. So right now, I'm just going to show this right here. So these 9 meshes, they're all static right now. So I'm going to hit play. So you can, not sure if you can see this clearly, but on the bottom right, this is the RTF value. So it's running at 90-something% real time. So which is fast because these are all static. So I'm going to publish a command in a separate terminal that you don't see here, but I'm going to do that now. And this makes it all dynamic. You can see the RTF dropped to 5%. This is a common problem that we see from users. You have meshes in the scene, it just destroys your performance. So I'm going to continue hit play. And when all these objects settle, when they stop moving, the RTF should bounce back up. But I'm going to visualize the context here a little bit. So show context. All right. Boom. Okay, so now the context is stable. You can see now the RTF has bounced back all the way back up to 90-something%. So these objects are auto deactivated. They don't no longer participate in physics simulation. So we worked on bullet-featherstone implementation with an eye for performance. So it scales better with a large number of objects and large number of contacts. So what you can do here is you can actually play around with this as well, and then you can play. And if I move it, so you see the contacts start popping in and out again, so it's unstable. The RTF drops, but as soon as it settles, the RTF bounces back up because they're deactivated. Okay, for completeness, I will show the same thing happening with Dart physics engine. Okay, so this is Dart. You can double check that in your component inspector. It says it's running the Dart physics plugin. So let's go back and hit play. So everything is static. It runs at around 100% RTF. And then I'll just publish a command to make everything dynamic. Now you can see the RTF drops. But Dart doesn't have this auto deactivation feature, so the RTF will just remain there. So in the same exact environment, the same number of meshes, it's going to suffer a little bit because meshes are always dynamic. So one thing that we usually do in the past is that we will if nothing is interacting with it, we'll try to make them static. Their code that we write to do that. But in Bullet, that does it automatically for you. All right, that's for my demo. Let's move on to the next presenter, Ben.
All right, let me share my screen here. All right, let me see if I can't pull this up. All right, can you guys see my screen all right?
Perfect.
All right, fantastic. So what I'm going to go first demonstrate is the recent addition that we had for doing material color changes. And basically, if you've ever had an object that you need to change, say, color for signaling, like LED lights that are letting you know what kind of status is going on a vehicle, for instance, mode changes or anything else of that nature, it was a lot harder to manage that dynamically from, say, ROS or any other application. So now you can directly control material color from a ROS message using ROS GZBridge or directly from a transport topic. Also, it applies to other things, like you can have translucent objects, for instance, like this over here. And an example of basically changing directly even from the CLI, you can take that translucent object, you can publish to the name of it, the entity name. In this case, it's an Ionic statue visual, and you can change it. So for instance, this time I'm going to change the alpha alta 1 on it. And voila, now you have a visual that you can see, and obviously you can change the color as well to any other color you want. Along the same lines of visualization, we recently added also a cone feature as a primitive shape. So you can write that both in SDF as well as you can do that in the direct shape drop tool right here. So I can move this shape, plop it down, for instance, over here. Maybe I don't like the color of this shape, just isn't my thing. So I can instead go back, change the color of the cone visual to, say, a nice glowing red. And voila, very emissive bright red. So a lot of things that you can do in a combination of those two. The other recent addition that we added was also the ability to control the camera a little bit better. For high and fast, well, for fast moving vehicles, typically the general P gain in Gazebo basically made the thing turn to a little microscopic dot. If anybody's flown drones around at high speed in Gazebo and you decide to follow it with the GUI, you have probably experienced that as well. And so now there's a whole bunch of configuration options and ability to do things. So for instance, I'm going to initially just start off by just following this vehicle. So this is sort of your traditional follow. This is what you would experience in the past. And if I drive this around, you can sort of see how there's some level of lag and the distance is sort of off for this type of environment. So now we have a camera tracking config that you can load into it. And with that, you can easily change, for instance, your follow distance. So let's get in a little bit closer here and let's set this to about 0.5. And as you also notice, though, this still has a lot of sort of, how to describe it, delay, lag. You're really not getting it in view when you're up this close. And even with this relatively small moving vehicle or slow moving vehicle, you're not really having it in good frame view. So if I decide just to bump up the P gains for the tracking and following all the way, now when I move, it stays locked on exactly where you expect it to. Now this is all great and good until you actually have the need to have something beyond that, such as you want to follow another object in the scene. And to be able to follow another object in the scene, for instance, I can choose to now look at this one over here. And, you know, okay, I'm looking at it, but the vehicle sort of seems off as I'm driving around. So instead, I can go here, center it on the vehicle. And now you get sort of that visualization with the vehicle. So no matter where this vehicle is driving, you're looking at that object and seeing basically where that's at. Also, you can now, anytime, of course, you can escape this by pressing escape. And as I go through a wall here, you know, You can also choose to track objects. So I'm going to track, for instance, this. Let's go here, just do track. So no matter where I move in the world, so I'm trying to move and change where I'm at, no matter how far away I go, I'm going to always be looking at this object. So you have a lot of new features, including also I could choose to track this instead. So wherever I'm at in the world, it's just going to look at that, no matter, you know, how I move and orient myself. So quite a convenient feature. The last thing I'll cover is we also recently added the ability to look at, let me actually zoom this up a little bit more, topic frequency. And this is really helpful if you're working, for instance, with hardware in the loop, or, you know, even doing software in the loop with, say, like POSIX, if you're running a real-time operating system and you want to see how messages are going across and the timing as you're driving the clock or other things like this. In this case, I want to see what the topic frequency of my actuators are being published in the simulation from my POSIX side that is controlling the actuators over GZ topic. And so for this one, I'm able to now see that I'm getting about 10 hertz average rate, and I can see what the interval is of that publication standard deviation, which really helps you to debug things, especially if you're getting really like large time skew and your deviations going up. So I think I covered everything in that one.
Okay, great, awesome. Now we move on to Carlos, who's going to be talking about 3 different things. It's going to be transport, logging, and also improve ROS GZ support. Go for it.
Thank you. Hello, everybody. Exactly. So I will start with a few updates related with transport. So the first one is an API change. Is related with how we can tune the scope of the publisher and subscriber. So in the same way, you can say, I'm interested on limiting the, these messages to my host or to my process. There's a new one called ignore local messages that I'm going to illustrate it with an example. If you look at the upper right window here, you see that we create a node here, and then after that we advertise a topic, who, then we fill a message, and then using the same node that we declared before, we subscribed to that topic, and then later on we go into an infinite loop publishing messages. So we just share the same node. So if we run that example, you see that we directly receive the messages. So as expected. If you look at the lower right window right now, it's the exact same example, but I'm highlighting here the new block. So we already had the subscription options, but after that, there's the new option. We set ignore local messages to true, and then if we run that, we don't receive that message, so we ignore that one. So yet another way to fine-tune your scope. The next one is we improve the ergonomics when you're using the transport from the command line. So in particular, we improved services. So when you're requesting no input services, when you're requesting one-way services, there are a bunch of things that essentially let you type less now on the console. So I'm gonna again show you an example to give you a taste of this. So imagine that you wanted to use like a responsor, like a no input service request from the command line. So first of all, let's run a service provider, on one side, and I'm gonna type or simulate the typing that you need to do that kind of service call. So we are requesting a service called quote, and this is again a no input service. That means we're not interested in sending anything. We're just interested in reaching that service and then getting a response. So far or until now, we had to say, hey, the request type is empty. The response type, sure, it's a string. And when we request, we need to pass that entry or that input parameter, but it's going to be unused. And then, of course, we pass a timeout. So if we do that, oops, we get the response that we wanted. Perfect. But it was a bit clunky. So with the new, I guess it's this one. With the new syntax, this one. With the new syntax, it's going to look like this. So let's do here, response or no input. And now instead, we can do same thing, GC service. We pass the service name, which is quote, but then we don't say anything about the request. It's completely implicit. We just say, hey, we're interested in a response type. That's a string. And we don't have to pass you anything like that. And of course, at the same time, we're not interested in passing a timeout. We created a default timeout that's going to work very well in these use cases from the terminal. So then we get the same response, but as you can see, the amount of typing is way less. So we did a bunch of these type of improvements in transport that we think is going to improve your experience in the console. The second improvement that I wanted to bring to the table was related with logging. So so far in all the previous versions, we had our own custom logging, and this was what you could what's making available to see all these debug messages when you were typing gcsim-b4, for example, in the console, or those debug messages that you could see in the logs of Gazebo, for example. So that was all completely custom code, and we wanted to improve that. Essentially, what we're doing for Ionic is we used a third-party library called Speedlock, and the main reason for doing that is because we want to reduce the amount of maintenance that we do on any code that we have in our code base. So we think this is going to be beneficial, and we're going to focus on other stuff and no logging when there are other people doing great work here. What is the logging now? So this is a new dependency, Speedlock, and we move it to, before it was in GC Common, but now we move it to GC Utils. The main reason for that is because GC Utils is a lighter library in terms of dependencies, and we think that logging is a feature that most of our libraries, across Gazebo, are going to need and are going to use. So we better depend on GC Utils than on GC Common. So what you can see on GC Utils is a very lightweight wrapper on top of a Speedlock that's will let you use pretty much all the Speedlock API if you want to. But then for compatibility reasons, we keep in GC Common the same API that we used to have. So the same macros, all the GC log, GC warn, GC err that we used to have, and the console class. So I'm going to show you a quick example of, here I'm looking at the lower right window. You can see here how we have GC trace, GC debug, GC messages. So all of the previous macros, there are two new ones, GC trace and GC crit for critical messages. We can always set the verbosity as before. We can set a prefix, and at the same time we can, so that's going to show all the messages in the terminal, and at the same time we can call init with a path, and that's going to specify the file where we want to log everything, on top of the console. So you can see that, I'm not going to enter into many details, but you can see that there are many messages now with colors. You can also look at the file that's created with pretty much the same interface that we used to have. In terms of performance, one nice thing about this is that Speedlock seems to work pretty fast. So you can see in this example, the interesting part is the y-axis. This is time, and this is a test that actually logs 10,000 messages and measures the elapsed time of doing that. So we run this experiment in Harmonic, and it takes about half a second. And then if we run the same experiment in Ionic with a new logging system, it goes a little bit over 100 milliseconds. So around 4 times faster, which is always good. And then finally, I wanted to talk about a third item here. We made a few improvements as well for during the last months in the way we interact with ROS. So all the ROS GC package, I think we polish it a bit, and I've divided the improvements into 3 different parts. The first one is that we created some launch actions for better integration into your launch file. So what that means is that we made available two new elements that you can use in your XML or your YAML or your Python launch files. One is the gc_server tag that accepts, a bunch of parameters, but the most important one is the world SDF file. That means the file that you want to load when you launch Gazebo. And in a similar way, there's a ROS GC bridge element that you can use to pretty much launch the ROS GC bridge at the same time. So you need to pass, give it a name, and also like a config file, which is a YAML file that has all the mapping between the ROS and Gazebo, all the topics that you want to bridge. So we think that with this is gonna all the launch files that you're gonna create are gonna look much better. Besides that, there's a second thing that we improved. We created some new launch files that you can use directly off the shelf to launch Gazebo, GC server, the bridge. You can use it to span models in Gazebo or a combination of this. So you can launch the GC server plus the bridge. So quick example here. I'm going to launch with one of these existing launch files. In this case, it's called rosgc_sim.launch. I'm going to launch GC server plus the bridge. So as I said, I pass a bridge name called rosgc bridge, a config file here with some, I think it's just one topic just for testing, and then a world. If we launch it, we see here that GC server is starting, and then we can check that it should be a chatter topic. Okay, it's now working, and of course Gazebo is running. So if we run it with the GUI, it seems to run. Next thing I wanted to talk about is related with composition. So when we created all these launch files, all of them have an extra parameter called use composition. So that let us run all the relevant nodes that we're launching in two different, I guess, scenarios, in two different configurations. So if we use composition, or if we set it to true, we are in a scenario like in the one on the right. So that means there's going to be a ROS container, and then every single node that we wanted to run is going to be loaded as a plugin inside that container. That means that we're going to use intra-process communication. Everything is going to be faster, no serialization required, and we're going to get better performance. So this is a good way to kind of group all the different launch files and get better performance. But it's flexible enough. All these launch files are flexible enough that you could decide not to use composition for your own reasons, and then you would be on the left case where everything are regular ROS nodes, everything when you communicate is serialized, and you're using normal inter-process communication. If we go back to our experiment that's running, we could check ROS2 component list, and you see that there's a ROSGC container, and the server and the bridge are loaded into that. If we stop the example and we run it again with use composition set to false, and then we repeat the same experiment, there's not going to be any components, and if we check list the nodes, then we're going to see that we have two regular nodes instead. And finally, just wanted to show you the results in terms of performance. So in this example, what you see on this plot is on the y-axis again time. On the x-axis is just a few iterations of the same experiment. And the experiment itself consists of publishing 1,000 images from Gazebo, bridge those images, and then there's a ROS subscriber on the other side receiving those images. And we measure how much time we take to receive the 1,000 images. So lower is better. On the blue line at the top, this is the result when the three entities are running as independent nodes. The orange one is the result when we're combining two into the same process, and then the green one shows when we use composition between the three of them, and you can see that we get pretty much like a half or double the speed up here. So this is all I had for today. So passing over to Ian.
All right, thanks. All right, now we have Adisu to talk more about the ROS GZ improvements and then also SDF. Go for it.
All right. I just want to add a few more points about Gazebo and ROS integration than what Carlos mentioned. The first thing is that GZ server or Gazebo is now a ROS node, and that's very important and has implications. One of them is that you can now launch it with a node, either XML tag or Python launch file function, instead of using an executable. It also means that you can compose it, so you can use composable nodes with ROS, as Carlos talked about. The implications of it being a node versus an executable is that previously with just running an executable with an external shell or whatever, the issue was that if your launch file crashed for any reason, it could be because of a Gazebo issue or a totally different issue, some other node caused your launch file to crash. It could cause that gzsim server, the backend of Gazebo, could stay in the background without being properly closed. And so when you run another Gazebo launch, this other server could cause, you have a duplicate Gazebo server, and that could cause a lot of issues. So this, making sure that that the signals are properly propagated is important, and that's what this allows you to do. The other thing it allows you to do is that it accepts SDF files or strings. This is something new we've added, especially with the string. It allows you to pass in something that was processed by a Zacro. So instead of having to create a temporary file and then passing that to Gazebo, you can now just do it on the fly, which makes launch files very easy. This also gives a lot more potential for even more tighter ROS integration in the future. One idea is that you can automatically load ROS-specific plugins, since we know that this is Gazebo running it with ROS, and maybe we could do automatic topic mapping or setting proper paths for ROS package ecosystem, which could make it easier to find resources in other packages, for example, mesh files or other plugins or other SDF files. So we're pretty excited about this, and we're gonna keep on pushing the, what we can do with more tighter Gazebo and ROS integration coming down the pike. What I'm going to show next is a more integrated example of what Carlos and I have talked about. So what I'm going to do now is just launch this demo. This is the TurtleBot for running inside the Gazebo Ionic demo world. I won't go into it in too much detail because we have a demo right after this that shows it off, but it has nav2 integration, and I'll be able to show you that I can estimate its pose and then send a gulp pose and have it move to the right, to the commanded position. And this is something you should be able to, once we have the Gazebo release, you'll be able to download and try it for yourself. So what I wanted to focus on, though, is that you can now, with the new launch files, with the new launch actions that we have, you can use them to simplify your launch file. So for example, the GZ server launch action can be used to start the backend, the Gazebo server, and you can give it the SDF file, and it's a very small and compact launch file. Instead of having to include launch files from ROS-GZSim, you can just use this action directly. What this also allows us to do is that you can use the action directly in your XML launch file. So if you're a fan of using XML launch files, that could be easy for you to do. Same thing for launching or spawning the Turtlebot 4. It's a big Python launch file, and on the left and on the right is the equivalent in XML. But what I wanted to focus on was that the bridge, we have a specific action for the bridge, and the ROS-GZ bridge. So this can take the bridge name, which is necessary to differentiate between other bridges, and then you just give it the config file and whether it's using composition or not. And the same thing can be done in the XML on the right, and it is same thing can be done on the XML on the right. You just have to use for finding other packages in their share directory. You just have to use the find package share function there, and yeah, otherwise it's the same arguments and it's very compact. And lastly, the overall launch file that launches everything. So it spawns this, it creates the world, or starts Gazebo, it spawns the Turtlebot 4. One thing I would mention is that the launch file that we saw that uses the GZ server action only actually starts the server, the backend. So you still need to use an execute process to start the GUI, and we will hopefully have a different action just to run the GUI, but for now you have to use this execute process. And so the same thing for the XML. We just include those launch files that we've created all in XML, but then you have to use the executable for the GUI. And I didn't know if you noticed, but the demo that I ran was actually using the XML launch file. Now I'd like to talk about a new feature that we've added, and that is supporting specifying plugins in SDF without overriding the default plugins. So in the past, the scenarios is like this. You're a new user, you come to Gazebo, you try out an example SDF file, and you want to add a camera, for example. And you learn that you have to add the SDF tags for a camera. You learn how to do that, and you put that in, and you start your simulation, and there's no camera, you don't see anything. Then you learn that you have to add this sensor system in order to use cameras. So you come in and you actually add this plugin to your SDF, and if you're unlucky, that would be the only plugin in the world. And so when you run the SDF file, what you actually see is a blank 3D viewport. Nothing seems to work, physics isn't running, it just seems very broken. The reason is Gazebo assumes that you're trying to override all the plugins. If you specify any plugin at all, it thinks that you're actually trying to override all of them and expects you to provide all the necessary plugins that you think you need. That includes physics, the user commands, the scene broadcaster. So in Ionic, what we've done is we thought that was a little bit less user-friendly, a little bit non-intuitive. So we've made it so that by default, if you add a plugin, it will also load the other additional default plugins that you could find in your .gz, in your home directory in the .gz folder. So now you just add the plugin and it will add all the default plugins for you. Here I'm trying to show how to use, how this wouldn't work in Harmonic, but I had a system issue with my system that made it not work. So I would now like to talk about how you can get back to the previous behavior. So if you're interested in controlling exactly what plugins are loaded, if you're an advanced user and you know what you're doing, you can set this policy called include server config plugins policy. And if you set that to false, Gazebo will go back to its previous behavior, which is to not load any of the default plugins for you. So you have to provide the plugins that you need. This is currently set to true by default in Ionic, but it will be, when it gets backported to Harmonic, it will be set to false. So the same new behavior of loading default plugins applies to GUI plugins as well. As you see on the left is the new Ionic changes. In the demo world, we only have 2 or 3 plugins, whereas on the right is what you need for Harmonic, which is to have all the plugins that that you possibly need that come by default, because you have specified that one plugin or a couple of plugins that you wanted in addition, or you wanted to modify the camera pose in the minimal scene, for example. One last thing to mention is that when loading these default plugins, if the plugin in the default set is also listed in your SDF file, Gazebo will not duplicate them. Instead, the one in your SDF file will override. And so, for example, here you could start a physics system. You can add a physics plugin and with the bullet-featherstone engine, and it will just override the one that was in the default set.
Thanks, Ian. Thanks, Adisu. So this is a demo to showcase the integration with MoveIt, nav2, as well as OpenRMF. Ideally, this would be a pretty good starting point for users to figure out how to integrate either of these pieces of software with their own Gazebo world. And as Adisu has already shown, we have added in a Turtlebot 4 together with its nav2 stack. So this is the nav2 stack, an example that is upstream on nav2 bring up. So we have ported it such that it spawns the same robot as well as its controls and nav2 into the Ionic Demo world. Plus we've added a little bit of a flare, like a tray on top of the robot itself. Next up, we have integrated a Panda robot arm in the world. So this allows us to use MoveIt and perform things like real-time planning as well as executing the trajectory control, controlling each of the joints in this way. Last but not least, we have integration with OpenRMF. On the left side, we can see what we call the traffic editor. So this is how we've drawn up the Ionic Demo world for OpenRMF. So you'll see that there's a bunch of lanes as well as named waypoints. And this is the OpenRMF web dashboard. So pardon the visuals right now. Usually we would use a floor plan of the building. But in this case, we are just using the laser scan of the robot. We can use it to visualize things like waypoints as well as robots and where they are in the world that we've integrated with. Another thing that we can do with OpenRMF is to send tasks, and these can be rather complicated tasks in general. So here we are sending a delivery task such that it goes to the bar, picks up a can of Coke, and then goes to a table and drops off that can of Coke. So usually we would have multiple robots in the world, but in this particular case, since we only have a single robot integrated in this world, the task will automatically go to this bot 4. So here's the task summary, and the robot is making its way to the bar. And as soon as it reaches the bar waypoint, RMF would trigger what we call a dispensing request, and in this case it's the robot arm dispensing the can of Coke. A fun fact is that we are doing this full grasping and pick and place motion fully using the friction in Gazebo, so we're not actually adding any detachable joints here. So that's pretty cool, and I guess it's a really good example on how users can actually achieve this in Sim. So the robot performs a preset number of moves and dispenses the Coke onto the robot. And when it's done, it will inform RMF that the dispensing request has been completed, and RMF would start commanding the robot to continue on to its job. So it will head its way to the table. For RMF Web, another cool feature we have is scheduling. So we could also schedule this same Coke delivery task every day at 3 AM for unknown reasons. But yeah, so this allows us to run scheduled tasks throughout the day during live deployment, for example. So the robot will make its way slowly to the table. You will notice that it's not going directly to the table, but instead following a preset number of waypoints here. That is because it is following the waypoints that we've drawn up in OpenRMF, which allows us to reason and negotiate between multiple robots and make them get out of each other's way when necessary. This is helpful in like narrow corridors and such. So the robot will reach the table and the task is done. You'll see that the Coke has been teleported to the table, and voila, it's gone again. So we have written a teleport ingester, which ingests the Coke onto the table, and when a few seconds later, it will teleport the Coke can back to the bar again. So this allows users to repeat delivery tasks in this particular demo if they so want to. Another task that we have is the very basic patrol task that we can get robots to do. So it just commands robots to follow a number of set of named waypoints such that they just navigate around the world. And that is basically it. So ideally this is a demo where users can have their first time experiences integrating like all these different pieces of wonderful software. And yeah, back to you, Ian. Thank you.
Alright, so the feature I'm talking about today is improving the determinism of the force-torque sensor. Just a reminder, force-torque sensors measure force and torque in a data structure called a wrench. Not this kind of wrench, but this is an important sensor, and by determinism we mean that you always get the data at the most recent data at the correct time. And this is important because force-torque sensor data is used in control algorithms involving contact and grasping, and they can often do it at a high frequency, so it's important to have the most current data. And so the way that we've improved that determinism, well, currently all sensors can in GZSim provide their data over GZ transport, which is pretty good, but there's a more deterministic way to provide that data, which is by writing it directly to the ECM. And so now I'm showing an illustration of an example world that demonstrates this feature. So we borrowed a demo world from the mimic, showing off mimic constraints from Harmonic, and there's several pendulums with mimic constraints coupling them, and when you and so for every joint in that demo world we added a force torque sensor, and for every force torque sensor we added a plugin that will measure the timestamp of the data coming out. It gets it both from GZ transport and from the ECM. And then it prints an error message in red if the data is out of date, or is, if there's a problem with determinism. And it's pretty good with GZ transport, but we've found, but there's threading that happens with GZ transport, and we found that when your system is under load, here we're showing when you run a stress command with 8 CPU thread workers, it generates a whole bunch of these red error messages, because having a system under load makes it more likely to have data that's slightly out of date when you're subscribing over GZ transport. But with the ECM you always get the most current data. Yeah, even just dragging the window gives a few error messages, but then once you actually run the stress command, it generates a lot of them. So this kind of just shows the reason for this feature. And the way that it's, in order to implement it, we had to change the way the force torque system is updating. So previously it was using the post update callback, which allows read-only access to the ECM and in parallel, but since it can't write to the ECM, we moved the force torque calculations to the update callback. And this also required adding a feature to be able to specify the order of execution for system updates. So we changed the physics system to run, because we want to make sure that the physics system runs first, and then we run the force torque system after that. And the way the system specifying the order of system order of execution, there's an integer priority value, it defaults to 0, and then we set negative values for physics and also slightly less negative value for the force, that's the post-physics sensor priority, and we use that for the force torque sensor. And since those are both negative, if you just add a new plugin, its update will run after both of those. And so that's, but you can also specify the priority for a system manually in XML. So it's a pretty flexible feature, and we've, yeah, both of these features have been used to improve the determinism of the force torque sensor. But you can, specifying the order of execution for systems could be useful in other applications as well.
Hi all, let's switch gears and talk a little about continuous integration. This is useful if you're developing using Gazebo and have a CI pipeline setup. We're going to look at the GitHub action called setup Gazebo. This action sets up a Gazebo environment by executing tasks like installing the dependencies, managing the repository keys, checking platform compatibility, and most of all, performing the installation of your preferred Gazebo distribution. All you have to do is add a few lines in your workflow YAML and you're good to go. So let's delve deep into it. The first example shows how to invoke this action from your workflow YAML using a default GitHub hosted runner. You call the action using the URL and tag like so. So you write gazebo tooling /setup gazebo @v0.2.0, where 0.2.0 is the latest release tag. This action needs an input parameter called required gazebo distributions, where you specify the gazebo distribution of your choice. Multiple distributions can be passed by separating them with white spaces. Next scenario shows the same example on a Docker container. So you do this by specifying container followed by the image name. In this way you get a containerized installation of Gazebo. Moving on, you can also iterate over all Gazebo distributions of your choice using the matrix functionality of GitHub workflows. So in this case, the 4 Gazebo distributions are specified, followed by the appropriate Ubuntu distribution. The matrix iterates over the list of distributions, spawning one job per Gazebo distribution on a specified Linux platform. Moving on, the same matrix scenario is shown using Docker containers instead of default GitHub hosted runners. Next, we move on to seeing how to install Gazebo from pre-release or nightly repositories using optional inputs. So these optional inputs are use Gazebo pre-release and use Gazebo nightly. By specifying either of them to true, the action will add the appropriate repositories to sources and perform installation of the distribution provided as input. Here we see an example of installing Ionic through the pre-release repositories, as Ionic has not been officially released yet. Next, we come to a very interesting part, which is installing ROS2 and Gazebo side by side along with ROS-GZ. ROS2 can be installed using another available GitHub action called setup ROS. While invoking setup Gazebo, an optional parameter install ROS-GZ is populated with the names of the ROS distributions. This will install the appropriate ROS-GZ version based on the available ROS2 and Gazebo pairing. Similar to how we specify multiple Gazebo distributions, you can also specify multiple ROS distributions and it will install ROS-GZ for each and every distribution that you specify. Moving on, this action is also available on other platforms, for example macOS. Here, the specified Gazebo distribution is installed through the Homebrew package manager. So the user need not worry about installing Homebrew, as the action takes care of installing it beforehand and then performing the Gazebo installation. Similar to Ubuntu, you also specify the Gazebo distribution of your choice. This action is also available on Windows and can be installed from Conda Forge using the Conda package manager. Due to this, it is necessary to install Miniconda before invoking setup Gazebo, and it can be installed through an action available on GitHub Marketplace called setup Miniconda. Next, we'll see an example of running setup Gazebo. This example will show installing Gazebo Ionic from pre-release and nightly repositories. As you can see, the distribution is specified. In the output of the action, you will be able to see that a pre-released version of Ionic has been installed. You can also see the previous terminal in which the action installs Gazebo Ionic. This brings me to the end of my presentation. Thank you for your time.